Hi, everyone. Welcome to Pulsar on the Lakehouse. My name is Addison Hyam, and with me, I have here Ryan Zhu, who's a staff software engineer at Databricks. Before we get started, we'll do a quick bit of introductions to Ryan and myself. We'll get started with Ryan introducing himself.
Hello, everyone. I'm Ryan Zhu, staff software engineer at Databricks. Currently, I'm the tech lead of Delta ecosystem team. I'm also Apache Spark PMC member and committer. Currently, I'm one of the co-developers of Delta Lake and Spark streaming projects. I have been working on these two projects since the beginning. Recently, I'm also working on Delta sharing, which is an open protocol. We are working to allow people to share data across multiple organizations.
Thanks, Ryan. My name is Addison Hyam. I'm the chief architect at Stream Native. I'm Apache Pulsar committer, involved for the last 7 years working on streaming systems, both Spark and Pulsar. I've been part of the Pulsar community for about 3 years now, where I previously led the implementation of a large Pulsar cluster at a company called Instructure. Happy to be here with you all today. And with that, I'll hand it over to Ryan to give a brief introduction into Delta Lake and Lakehouse architectures.
Today, I'm pretty excited to have the chance to talk about Delta Lake and Lakehouse. Before we jump into Lakehouse, I would like to talk about the challenges people are facing today. Data infrastructure is too complicated today and very expensive to manage for advanced use cases. Many systems are not open. They are using proprietary formats. And you need to copy data around many systems. Different teams are not well connected to collaborate. This is one classic architecture example of this complicated data infrastructure. The massive majority of data is flowing into a data lake. Companies do a lot of data validation so that they can serve data science and machine learning on top of these data lakes. At the same time, a huge amount of data is ETLed to many downstream data warehouses to do BI and other use cases. We have to do that because the BI workloads are often too slow to run on a data lake directly. Depending on the workload, data also need to be moved out of data warehouse back to data lake if it's been updated in the data warehouse. Increasingly, the machine learning workloads are also reading and writing to the data warehouses at the same time. And it's pretty complicated to keep data lakes and data warehouses in sync. The root cause of the problem is inherent difference between data lakes and data warehouses. On one hand, we have data lakes that do a great job supporting machine learning. They have open formats and a big ecosystem on top of them, but they have poor support for BI and suffer complex data quality problems. On the other hand, we have data warehouses that are great for BI applications, but they have limited support for machine learning workload. And they are proprietary systems with only a single interface. Unifying these systems can be transformational in how we think about data. This is why we are such a big believer in Lakehouse to provide one platform to unify all of your data, BI and UI, and AI to allow all members of the data team to collaborate together. By definition, a Lakehouse is based on open standards and open source. Because without being open, it's impossible to create the unification across all data types, all these tools and workloads. And the community for the best open source projects to enable the Lakehouse are in the audience today across such as Apache Spark, Delta Lake, MLflow, and Redis. The foundation of your Delta Lake is Delta Lake. Delta Lake allows you to build a data quality framework for your data lake by ensuring the data is reliable for ACID transactions. In this model, data is flowing into Delta Lake from all various of data sources, such as Pulsar, Kafka, and for example, Apache Spark has Presto. The data quality is improved incrementally from low data, intermediate data, and golden clean data. Then downstream applications such as machine learning, AI, and BI can build on top of the clean, fresh, and reliable data to fit the use cases it's intended for. Delta Lake is the foundation of this model because it's an open source project that enables building a Lakehouse architecture on top of existing storage systems such as S3, ADLS, GCS, and HDFS. Today, Delta Lake is used all over the world. Over 350 petabytes data per day gets processed on Delta Lake in Databricks platform. 70% data scanned on Databricks platform is using Delta Lake. And Delta Lake has been deployed to over 3,000 customers in their production Lakehouse architecture. So what key features that Delta Lake provides to help you build your Lakehouse? Delta Lake provides ACID transactions to support concurrent queries and guarantee snapshot isolations so that people don't need to worry about concurrency. It also provides scalable metadata handling to process tables with billions of files. It also provides data versioning, which supports the ability to time travel. Data is stored in open formats to allow users to leverage existing tools to read data from your Delta Lake tables. In addition, Delta Lake unifies batch and streaming queries, makes it very easy to write batch and streaming applications. Delta Lake also handles schema validation to prevent bad records from causing data corruption issues and support schema evolution. It allows you to audit history through transaction logs. Delta Lake also supports DML operations such as update, delete, and merge so that you can modify your Delta Lake tables very easy. We also continue to improve Delta Lake for more use cases, and there are multiple exciting features coming very soon. Delta Lake will allow users to drop a column or rename a column. You will be able to replace a portion of data in your table with new data atomically. merge command will get better schema evolution support and generated column support. In addition, we also plan to reduce our release cycle to make a release every 3 months so that people can get the new Delta Lake features quickly. Moreover, the Delta Lake community is interested and excited to expand Delta Lake and make it available everywhere. We are building the Delta standalone project to allow users to read and write Delta Lake natively. This is the foundation project we are building in order to enable the whole community to build a lot of connectors for different systems. For example, Pulsar, Flink, Presto, and we are actively working on these connectors in order to support them very soon. Next, I will hand over to Edison to talk about the work of Pulsar connector for Delta Lake.
Thanks, Ryan. Really appreciate that introduction into Delta Lake and Lakehouse architectures. Now I want to spend a little bit of time talking about how Pulsar and Lakehouse together can really simplify your data infrastructure and why they fit so well together. Before doing so, I want to highlight a few features about Pulsar that really make it a great fit for Delta Lake and Lakehouse architectures. So first, Pulsar is the unified messaging and streaming platform for real-time teams. It's really designed to allow a broad range of different teams to interact with real-time data. And a few features I want to highlight are Pulsar's ability to handle both streams and messages to support more workloads. So you may have traditional messaging workloads, work queues, etc. Integration between microservices that Pulsar supports very well as ordered high throughput streaming use cases that Pulsar also can do within that same cluster, allowing you to have more workloads once again on the same underlying infrastructure. Similarly, Pulsar's ability to support multi-tenancy, to have different teams, different applications share the same underlying infrastructure, allows it to break down data silos and ease data ingestion between different applications. And finally, Pulsar's georeplication support allows it to span multiple clouds and really be a underlying infrastructure to support global businesses. And this is a really great complement to Delta Lake, which Delta Lake, as Ryan mentioned, is really about supporting a unified system for data analytics and ML, which goes hand in hand with Pulsar's ability to support real-time data across a broad range of use cases like streaming, messaging, microservices. And so Delta Lake and Pulsar together are really two technologies that simplifies data infrastructure across your entire organization. I'll speak more to use cases and how we enable that, but before doing so, I want to spend a few minutes talking about what this looks like in terms of the integrations and connectors between these different systems, and really give you an insight into these first steps in really establishing a great ecosystem between the Pulsar and Spark Delta Lake communities and the systems that we're collaborating to build. So first in that is the Spark Pulsar connector. This connector has been around for a while. It's been used by many organizations in production, but it allows for you in your Spark applications to read and write data from Pulsar using both the data frame and data stream APIs. It's schema aware of Pulsar schema and also is very flexible of being able to output data to other systems, which we'll see in a minute. And this can be found at the Stream Native on GitHub and the Stream Native organization of the Pulsar Spark repository. And actually discussions are in progress for upstream contribution to make it even easier for you to use Pulsar on your Spark applications. And also kind of what Ryan spoke to, these newer developments, and specifically in the form of the Pulsar IO Delta Lake source. And so if you're not familiar with Pulsar connectors, a Pulsar connector is a managed component that can either run in your Pulsar brokers, embedded in your Pulsar brokers, or as a pod in a Kubernetes cluster, allowing for a fully managed sort of compute runtime for getting data in and out of Pulsar. And one of these that's in development is this Pulsar IO Delta Lake source built on top of the Delta standalone project. Speak a little bit more about how that works in a minute, but and what that enables. But this is in progress, and you expect a first release this year in the coming weeks. Okay, so now let's talk about this a little bit more visually and give an idea of the sorts of use cases that these integrations and connectors enable. Okay, so first off, let's talk a little bit about Pulsar. So as mentioned, Pulsar, and through Pulsar's native protocol, which is designed to support unified messaging and streaming. So that means if you have microservices you're connecting together that you want to do work queues or other messaging workloads, Pulsar fits that well as high throughput parallel distributed streaming. But that goes beyond just Pulsar's protocol support. Pulsar also has a component called protocol handlers that allows for it to seamlessly speak other application protocols or messaging protocols. For example, Kafka on Pulsar allows for, in your same Pulsar cluster, Pulsar to natively understand and interpret Kafka protocol and messages, allowing you to seamlessly use existing Kafka applications. Similarly, in sort of the messaging space, AMQP on Pulsar allows for RabbitMQ applications, AMQP 0.9, and in the future, AMQP 1.0, to seamlessly integrate with Pulsar for many existing messaging workloads that you may be having using the AMQP protocol. Beyond just the protocol handlers, there's also the aforementioned Pulsar IO Pulsar connectors framework. So this includes both source and sinks for getting data in and out of Pulsar. Here, we're just going to highlight a few sources. For example, we have the change data capture source, allowing for a Pulsar connector to seamlessly connect to a database, get a change feed, and write that into a Pulsar topic. Integrations for other systems like RabbitMQ, SQS, allows for getting data out of those systems also into a Pulsar topic. But many other source connectors and sync connectors exist for a broad interconnectivity between a set of systems. Okay, so moving on, we'll talk a little bit about the Delta Lake and Pulsar connector. So once again, this is allowing for data to be exchanged between Delta Lake and Pulsar with very high fidelity. So that means in near real time with schema data being attached, which makes all of your data in Pulsar available to any teams that are using Delta Lake to write applications. And then finally, the Spark Pulsar connector. Once again, this allows for developers to write a Spark job that can, say, read data from a Pulsar topic, transform that data, maybe write it back out to a Pulsar topic. Okay, so now let's spend a little bit of time talking about some of the use cases and really simplifications to your data infrastructure that these components allow. So suppose that we have a machine learning team that has chosen Delta Lake as their main way of getting data in and out. They're able to read training data from there, maybe even write back results from inference back out to Delta Lake. And so, but we have our application teams that are using Pulsar for interchange between microservices. And we want to get that data for usage in a machine learning application. Suppose we have some sort of recommendation system, for example. So now with the Pulsar Delta Lake sync, we can get that data seamlessly out of Pulsar into Delta Lake and accessible to our machine learning teams without them having to change their point of integration of interacting directly either with Pulsar or with those applications, really simplifying, not having to have a broad range of different ATLs, for example. But it's not just getting the data back out. As mentioned, we maybe want to get data back in. Maybe we have results from inference that we want to write in, that gets written into Delta Lake, and we want to make that available to our applications through the Delta Lake, or excuse me, the Pulsar source, reading data from Delta Lake back into a topic. Now we've made that data look like just another microservice or another topic that exists in our infrastructure, serving data just like normal, although it came from machine learning written into Delta Lake first. Okay, so it's more about not being able to just get data out of Pulsar into Delta Lake. Through the integration with Spark, you can use the Spark ecosystem to transform and enrich your data. So for example, suppose we have a change data capture source running that's getting a raw row level data into a Pulsar topic. And that data is maybe not a great fit for exposing directly into Delta Lake. So instead, we use a Spark job, reading that using the Spark structured streaming, transforming that, aggregating, etc., and writing that out to Delta Lake in a format that is better suited for exposing to external teams. So once again, we can use the fact that we can read from Pulsar and using the Spark connector and have Spark's great integration with Delta Lake to get that data in via that mechanism with some higher fidelity. And finally, is a kind of another idea is if you're really into the Delta Lake ecosystem, there may be some sources that are not yet available to get directly into Delta Lake, and Pulsar and its capabilities can sort of facilitate that. So for example, suppose you have data stored in SQS that you want your data science team to be able to make use of. Instead of having to work with that data science team to directly pull that from SQS, we can instead use Pulsar as sources, get that data into Pulsar, and then have that be written out to Delta Lake via the Delta Lake sync, and once again, made available to that data science team. And so hopefully this gives you a quick idea of how with these different components interacting together, we get a different infrastructure that can really solve to a broad range of use cases, both through Pulsar's broad capabilities in the real-time messaging space, and Delta Lake for its really great on-disk format that is open and easily integrated with many different applications. Okay, so to speak a little bit about how this works under the hood, want to just highlight this Delta Lake source and what it does. So once again, the goal of this is to be able to users to ingest Delta Lake changes into Pulsar without running a separate component. And as mentioned, Pulsar sources can either be run embedded, fully managed sort of in your Pulsar brokers or as a Kubernetes pod, allowing for you to not have to run a separate component or the complexity of deploying that. Instead, it's easily integrated into your existing Pulsar infrastructure. And what happens under the hood here is that this is built on top of the Delta standalone library, which interprets a metadata change, which can be composed of either a new file or move file or some other change such as a schema change. And in the case of where that's a new file or move file, that takes the form of a Parquet file, which we read, parse the records out, and then write those individual records to the underlying topic. In the case of a remove file, where those records actually act as a tombstone, indicating that that record's been deleted, and then we can interpret that in our topic as that record being deleted. But it's not just about the data, it's also the underlying metadata that we want to keep in sync between these systems. And so if a change comes in that updates schema, that will actually result in the Pulsar schema registry being updated with that schema for that topic, allowing you to have a really easy and seamless integration of unified schema between these different systems. That's not only just on the source side, also in the upcoming sync that will be early next year. Also, if you have a topic, a Pulsar topic that has schema, when that gets written out to Delta Lake, that will be written out with a obviously Delta Lake schema compatible format, giving you that really seamless view of your data across these different systems. Okay, so we're really excited about this work already with Delta Lake, but this is really just the beginning. So I want to spend a minute talking a little bit about where we're going next. And if you're not familiar, one of Pulsar's unique features is its tiered storage. This allows for your streams to be offloaded out of Apache Bookkeeper. We're using Bookkeeper for low latency, high performance writes, but we may want to offload that into something like S3, Google Cloud Storage, Azure Blob Storage, HDFS, etc., for long-term storage of streams. And currently that is done in a format that's not easily accessible by applications once it's offloaded. But work is actually in progress to offload that data in a Delta Lake compatible files with all the required metadata, which allows for Pulsar to make its streams available to other applications via the Delta Lake format without any need to actually have an extra copy of that data. Pulsar can still use that data for serving its streaming use cases, and other applications, Spark, etc., can directly read from Delta Lake. That's something we're really excited about to further simplify and realize the Pulsar's potential as a system that supports a broad range of use cases. And stay connected to learn more, and we'll have more to share on that in early 2022. So to sum up for today's talk, once again, the Pulsar and Delta Lake are technologies really designed to simplify your data infrastructure. With the ever-changing growth and needs around data and different use cases, it's really important to invest in and look into tools that can integrate well and simplify the broad range of needs there. And so if it's interesting to you, if you want to learn more, connect with us in the Connector Pulsar in the Delta Lake Slack to learn more. And we're really excited for any of you who are interested in this and to engage and come get involved in the Pulsar and Delta Lake communities. And finally, I just want to thank everybody for your time and attendance today, and also encourage you to stick around for the conference. There's going to be a lot of great talks to talk more about Pulsar and its ecosystem and integrations, as well as a lot of interesting use cases of teams that are succeeding with Pulsar. So thank you again, and enjoy the rest of the conference.